Hello, AP Physics students. This is Mr. Kennedy. I hope everybody's doing well. We're going to start today with our first review. This is going to be our review of two units, Unit 8 and 9 in electricity and magnetism. And Unit 8 was about electrostatics, and Unit 9 was about Gauss's law. And I just want to go over some of the major ideas in both these two units, and just to give you an idea of some things you can get ready for, and then you'll take a look at a little AP problem at the end of this. So let's actually jump right in. First of all, with unit number 8, it was electrostatics. And some of the main ideas here were really conceptual ones. And the conceptual ideas, the main thing that we had was that electrons are the things that move. It was not actually positive charges. There's not protons that are moving around within many of the structures that we have. It's really the electrons that move. So when you have something that becomes negative, that means electrons were added to that object. When something that becomes positive, that means electrons were taken away from that object. We should be always thinking about the idea that electrons are the things that move. And then you have simple ideas like charges repel, and opposite charges attract. But you have to be a little bit careful with that. And that's because of induction effects that can happen. So even though like charges repel and opposite charges attract, we know that's the case, you can have charges attract to neutral objects because of induction effects that happen. And a typical example is if you have a balloon that you rub on your head. If you rub that balloon on your head, and then what happens is, on the side that you rubbed it, you end up having some negative charges deposited on that balloon. But that balloon will stick to a wall. And that's because inside the wall, even though the wall is neutral, that what you can have is that the electrons will move over slightly, and then what you have is a slightly induced positive charge on here. So even though you have like charge repel and opposite charge attract, be careful with induction effects. You can have things that are induced, charged and induced. So for instance, negatives can attract to neutral objects, and so can positives as well. So there's some a few basic rules in the beginning. That induction effect also plays a key role in something like the electroscope. If you have an electroscope here, and here's the probe of it, and let's say the electroscope is just neutral, so it's got as many positives and negatives all over it, but I bring a negative charge up to it. Well, what will happen then, if I bring the negative charge up to this, negative charges will flow down to the leaves, and the leaves will separate. The object still is going to be neutral, but you see that you have a little bit of this induction effect because the charges separate. Remember, you can separate charges, you don't create charges. So it's not like we're making charges whenever we rub the glass rod with silk or rub the amber rod with fur. We're not actually doing that. What we're doing is we are just separating the charges. And it's again by those electrons that are moving. Another big idea that comes in here is that you can shield from electric fields and charges. And the typical example we would give is in a car with a metal frame, because what will happen is if you have some kind of metal box, that if you were to put charges on it, the charges will remain on the outside. They'll try to get as far away from each other as possible, so those charges remain on the outside. So that means that the electric field will be zero on the inside. And like we said with the car, that means it can be relatively safe inside a lightning storm if you have a metal frame on your car. So the basic things you should think about in the beginning of electrostatics are really conceptual things. The electrons are the things that move, like charge repel, opposite charge attract. Things can be induced, and that you can shield from charge. Those are some of the big things. The mathematical things that came up, are really about forces and electric fields. And the forces involved are going to be given by between two charges. The old version, back from honors physics, was kq over r squared. And the version I like this year is q over 4 pi epsilon naught r squared. But keep in mind, it doesn't matter which one of these you use. They'll both give you the correct answer. So I like to use this version for when I have numbers involved, and this one when I have symbols involved. And don't forget that k is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So this is what happens when you have two charges and they interact. Now, my advice to you is to leave the signs out of these equations. I wouldn't put the signs in. What I would do is I would just figure out which way it moves and then go from there, and then give it a direction that way, because these are vectors. Now, in that same vein, what we found was something called the electric field, and the electric field is the force per charge, and it's kind of a strange thing to get involved with, but the electric field is the force per charge. And I would really make sure you understand in your own mind what the electric field is. But given that that's force per charge, then the electric field would be either kq over r squared, or it would be q over 4 pi epsilon naught r squared. Either one of those. Again, this is also a vector quantity. So because it's a vector quantity, what you should do is figure out which way it moves, and I would not put the signs in here. For scalar quantities I would, but these are vector quantities, I would not put the signs in there. I would just ask yourself, which way does it move? Especially when you're looking at combinations of forces and combinations of electric fields. Put the direction that it moves and the direction that it would be overwhelmingly the bigger one. Now, here's another part to this. Although we talk about the fact that electrons are the things that move, the electric field is defined as the way a positive charge would move. And remember, we called this the steepness of the hill. Later on, we called voltage the height of the hill, but we called electric field the steepness of the hill. So the basic concepts involved in electrostatics, and then only a few equations. Now, we did a lot with these equations. We actually derived what the electric field is of a disk and a ring and all kinds of other things. But I think the concepts are the most important things to deal with first. So you may want to check out the conceptual manual as you're doing it too. So that was Unit 8, electrostatics. Unit number 9, we spent a lot of time on only one equation. And the one equation was really Gauss's law. Now in Unit number 9, Gauss's law, it was really one thing. It was the integral of E dot dA is the sum of all charge over epsilon naught. Now, both sides of this equation are the flux. This is the electric field that passes through an area, so that is the electric flux. But also, the amount of charge inside of that area divided by epsilon naught is also the flux. So both of these are the flux. Only the charges that are inside of the flux will actually contribute to that. But what I really recommend you do for this one is go back, take a look at our special chart for this. There are really only going to be 3 possibilities that you're going to deal with, and they are spheres, cylinders, and then parallel plates. Chances are, if you're going to have a more complicated question, it's going to be involved with spheres and cylinders. But the chart outlines a few things. This side of the equation, if you have a sphere, this side of the equation is going to be E 4 pi r squared. And remember, I call that little r because little r is where you are. On a cylinder, this side will be E 2 pi RL. One of the most common mistakes that people forget here is they forget that L. And for plates, this will be E times A. So these things, again with the small r, these are the integrals that you have here. It's rare that you actually take the integral. This is the electric field being constant in all of these cases, And this is the area. The area of a sphere is 4 pi r squared. The area of a cylinder is 2 pi r L. And the area of the plate is just A. But then on the other side, you can have all kinds of different things, and you should be prepared for any of them. On a sphere, the main things you'll have are just charges. That could be one possible thing. You enclose a certain amount of charges. Maybe you have to add and subtract them depending on what you've enclosed, but that's a possibility. The other thing you could have to do is some kind of ratio of the volumes, where you have pi r, or 4 pi r squared over, or sorry, 4/3 pi r cubed over 4/3 pi big R cubed, or something like that. You do have to do a ratio of the volumes. But one thing you should be prepared for is that they give you a non-constant rho, that some density with the charges is going to be changing with respect to the radius. If that's the case, this is going to be the integral of rho dv. Now, how do you know what dv is? Well, there's a quick way to figure it out. dv will be 4 pi r squared times dr, because you're going to integrate an entire sphere. And if you're integrating it, you integrate the surface area over that piece. So this gives you a clue as what to put here. So for a sphere, this dv is 4 pi r squared dr. For a cylinder, you're going to take a look at things like lambda L as the charge, or different combinations of that. Maybe you have some negative 2L, positive L, etc. You could also have a ratio of the volumes that you could put in here. But then you could also have, again, some non-constant rho, rho dv. In this case, what is this? Well, rho could be any function they have here, but dv, you look over here to see as a clue for what dv is going to be. dv would be 2 pi r L, that's the surface area, times dr, and then you integrate that. Because if you integrate that, you get pi r squared L, which is the volume. So these are things I would absolutely make sure that you've tried those. And we did a large number of those when we actually practiced them. For the plates, the plate is pretty easy. The charge on that is going to be sigma times the area. So with Gauss's law, I would absolutely make sure you practice some of these types of problems as you do it. But the whole unit came down to one equation. The equation was the integral of E dot dA is the sum of all charges over epsilon naught. And then it's just knowing what piece to put in, knowing what kind of shape you're going to deal with. Again, I would be ready for the sphere and the cylinder. Those are the more common ones you would take a look at. All right, so what you should try right now, I left a little problem on the calendar, is electricity and magnetism, 1998, number 1. The solutions are on there too. So go ahead, try that one out. It's got a little bit of electrostatics. It's got a little bit of Gauss's law in it. And then feel free to email me with questions. All right, hope you have a great day, everybody. And we'll do a little bit of review like this for each of the units, and then some practice for you. So time to get started getting ready for that AP test. All right, have a great day.